cases of aortic stenosis. Now we're asking about family history of heart disease. 42 of the cases have a family history. Among the 269 people, control group number 3, only 53 had a family history. The odds ratio we get here is 2.7, suggesting that family history might be a strong risk factor for aortic stenosis. Maybe the reason we're getting the number 2.7 for odds ratio is that these controls have measurement error in. Maybe some of these 216 people who we classify as not having a family history of heart disease really do. If they did, this 53 would become larger. This odds of exposure among the controls would become larger. Odds ratio would become smaller. So maybe we have a bias result even when we use control group 3. Bias in terms of information bias. So that's what bias refers to, a mistake in the design of a study, either due to selecting the wrong people or making mistakes on measurement. And that's a serious problem in any study design, but it's more serious in terms of selection bias in case control studies. And in terms of information bias, it's potentially a problem in any study design. So keeping that in mind, let me talk about the other problem that we epidemiologists face, which is namely confounding. And let me introduce this by asking you a question. Suppose you were doing a cohort study. You wanted to see whether smoking causes coronary heart disease. And you observed that your smokers had twice as much disease as your non-smokers. But then someone told you that your smokers are older people, and your non-smokers are younger people. So really what you observed was twice as much heart disease when you compared old smokers to young non-smokers. So there are two differences in these two groups. The smoking group has two bad things going for them. They're smokers, and that's probably a bad thing for you in terms of increasing your risk of heart disease. But they're also old, and we know that heart disease occurs more often among older people than among younger people. So it's the twofold increase in the incidence of coronary heart disease among the old smokers due to the fact that they smoked, or due to the fact that they were old, or due to both factors. And that's what we think about when we talk about confounding. So let's suppose this was our data. We had 1,000 smokers, 1,000 non-smokers. 240 of the smokers developed coronary heart disease, and we followed them for 10 years. 120 of the non-smokers developed coronary heart disease. The risk of heart disease in 240 divided by 1,000, that's 24%. Among the non-smokers, it's 120 divided by 1,000, that's 12%. The ratio of those, the risk ratio would be 2.0. But does 2.0 mean that a smoker's risk is twice that of a non-smoker? When I told you that the smokers were old, let's suppose that of these 1,000 smokers, 60% of them were old. Among these 1,000 non-smokers, only 20% of them were old. What happened? Let me say, suppose this is what happened. When I divided my data set into old people and then separately into young people, here are the 60% of the 1,000 smokers. 600 of them were old. Here are the 20% of the 1,000 non-smokers. 200 of them were old. And now I'm going to compare the 600 old smokers to the 200 old non-smokers. This is a subgroup analysis, just including old people. Any difference between the smoker row and the non-smoker row in terms of their incidence of cancer or incidence of heart disease, excuse me, this is a typo, cannot be blamed on age, because everybody in this table is old. So let's suppose of these 600 old smokers, 180 of them developed disease. Among the 200 old non-smokers, 40 of them developed disease. That means a risk of 30% among the old smokers, 20% among the old non-smokers. This ratio now is 1.5. If I had 1,000 smokers to begin with, and 600 of them were old, that means 400 had to be young. If I had 240 cases of disease occurring among all 1,000 smokers, 180 of them were the old people, that means 60 of them would have to be the young smokers. And likewise, I'd have 800 young non-smokers, and I have 80 cases of disease among them. The risk ratio among the young people, if we're comparing a risk of 15%, 60 over 400 among the young smokers, a risk of 10%, 80 over 800 among the young non-smokers, Again, I get a risk ratio of 1.5. So what's happening here? When I just look at young smokers, young smokers compared to young non-smokers, I get a message that the risk ratio is 1.5. If I compare old smokers to old non-smokers, I get the message the risk ratio is 1.5. No matter what age group I look at, smokers have roughly a 50% increase in their risk of getting disease, a risk ratio of 1.5. So I could say the right answer would be smoking increases your risk by a factor of 1.5. That's the number I see when I look at the young people separately or the old people separately. I could call that number the adjusted risk ratio. And why am I getting a different answer in the crude analysis when I compared all 1,000 smokers to all 1,000 non-smokers? That the smoking group had two bad things going for them. They had a risk that was 1.5 times that of the non-smokers. Their risk was higher because of them being smokers. But 60% of them also had another reason for having high risk of disease. They were old people. What we have here in this risk ratio of 2.0 is the combination of the effect of smoking, risk ratio 1.5, and on top of that, the effect of old age, because the 1,000 smokers have both of those effects working among them. And that's what confounding refers to, the mixing of two effects, the effect of the risk factor of interest, smoking, and the effect of the other factor, the confounding factor, older age, being more common among the smokers than among the non-smokers. Conceptually, what's happening here is, remember the ideal study? Take our smokers, measure their actual outcome, 240 of them got disease, put those smokers in a time machine, bring them back in time, stop them from ever smoking, see how many of them would have developed disease. That's what we'd love to have. We can't measure these counterfactual outcomes. They're hypothetical. They can only be imagined. They can't be measured because we don't have time machines. So how do we estimate these counterfactuals? How do we estimate how much disease would have happened among our 1,000 smokers if they had never smoked? We use another group, some non-exposed people, some non-smokers, to see what happened to them. But we can only use them if they're comparable. And in this study, the 1,000 smokers were not comparable to the 1,000 non-smokers. The non-smokers were younger. And that's the problem. We couldn't exchange the outcomes among the non-smokers to estimate what would have happened to the smokers had they never smoked, because the non-smokers were younger than the smokers. So, pictorially, what does that mean? This is our problem. We want to know whether smoking causes coronary heart disease. We want to know about the existence of this top arrow. Problem, we have this other factor, age, which is related to smoking in our data set. Smokers were older than non-smokers. And age also brings with it higher risk of developing coronary heart disease. So in this data, there are two mechanisms that could explain why the smokers had worse outcome than the non-smokers. Smoking themselves can increase your risk, and the smokers being older age also among the smokers than the non-smokers. So this is a diagram that describes the mechanism by which confounding by age could lead you to a wrong result, lead you to a risk ratio that's not 1.5, but bigger than 1.5. In this case, pathways that could lead them to having more disease. Direct pathway, the direct effect of smoking, risk ratio 1.5. For older and older age brought with a higher risk of disease. So let me give you another example of a confounder. I'm going to use that same example we just looked at, the acculturation example. And this is, let's suppose this is truth. Let's suppose we have no bias, no information bias. We have 86 people whose true prevalence of disease is 27.9. We have 382 people who are in a different group, integrated, who have a prevalence of disease of 15. So we observe a crude risk ratio of 1.8. The prevalence among the traditional group is